you.
Thank you.
So we're talking about complex models with very high dimensions of inputs, outputs, with submodels. So I'm going to try to discuss some techniques in order to reduce the complexity or the dimension of these models. And it's definitely part of the uncertainty quantification endeavor of trying to propagate uncertainties or calibrate models against observations, etc. I won't be able to cover a lot of that, but I can start with the basics. So if we want to replace a computer model, and I can use my mouse now. If you want to replace a computer model by a statistical surrogate, so a statistical object that mimics the input-output relationship, you can exercise the model at some values here, there, here, and then get an output and try to make inference about the actual input-output relationship from this computer model. And you can do that with using the Gaussian process technique, but other techniques are available. And if you do so nicely, you get uncertainty about your own predictions or your own approximation of the input-output relationship of the computer model. So that's one of the basic tools in uncertainty quantification, a surrogate model or an emulator. The problem is that not only it's not a problem, but it's popular, but it requires a little bit of thinking in terms of what are we doing here? We're drawing some uncertain function, and what I showed you earlier is one-dimensional input. If I go back to it, one-dimensional input, one-dimensional output. So that's relatively simple. But when you start having inputs that are entire surfaces or fields, a complex set of parameters and outputs that can be also in the same of the same type, this is a bit more complex. So this is the general setup, and in terms of statistical description, it has these Gaussian processes have a mean. They are not necessarily normal or Gaussian, right? What I mean by that is that a projection conditional on the observation is normal, multivariate normal. So a mean function and a covariance function that are the key elements of that Gaussian process, and we have those parameters. Now we have to make some choices about these functions. So these are either the mean, if we know something about the mean variations of a computer model, then it's better to use a mean because you can soak up already some of the variability. If not, you can just use a mean 0 or a mean some constant. But the covariance structure is really the one that's supposed to learn. It's a machine learning approach, obviously, as well. It's supposed to learn about the dependence across the inputs and in terms of the resulting output. So this is what we have here, the Matern covariance function. Here is one of the key possibilities for the covariance structure that helps you learn. So if you do that, we have to fit, as I said earlier, all these parameters in order to fit this Gaussian process. I'm skipping the details here, but it has a cost to fit. So the typical cost is n cubed for the fitting, because you have to compute some determinant or inverse of a symmetric matrix. So there are many solutions, or I'm just citing here my own work, but others have contributed to solutions, obviously. Dimension reduction we will discuss a bit today, but a smaller design, how many points and where should they be in order to get the same level of approximation but cheaper, and a smaller number of points is better. Using multi-fidelity approaches, multi-level, multi-scale. Hardware, if you're smart about the implementation of these algorithms on GPUs, we have a package now that is accelerating 250 times on GPU, but it's comparing apples with oranges. it's not that much faster. FPGAs, we're starting ExCALIBUR, the STFC kindly funded hardware and enabling software consortium with Edinburgh and Warwick. The EPCC in Edinburgh will host it, and we are going to give access to whoever is interested in using these very interesting types of chips that you can redesign in order to fit better the algorithm. We're going to work on that, and we have started. Linear approaches, smart moves. I organized a workshop in August 2019 at the Alan Turing Institute, and there's a video of many types of approaches and many types of thinking. So I'm going to start by discussing one possible type of dimension reduction is when you have an output that's a time series, an entire time series. So here, it's an example that's actually very realistic. It's the possible future tsunami occurring off the coast of Canada and Northwest Pacific USA. So this is the Cascadia region. The last tsunami was 1700, 26 January. It was extremely large, but it obviously not as much, not as many people lived there, and obviously it was a very different situation. So, but the next one may be very harmful. So if we vary the type of input, the type of source, earthquake source for this tsunami, and we display here the tsunami wave at this particular virtual gauge here, and at this other gauge, you can see the type of shapes that we get, and these are quite complex. Some of them have kinks and have sharp variations. These are due to the signature of the bathymetry. The flow, the tsunami wave flows over some bathymetry bounces in this strait. So what if we want to emulate the whole time series? So this is just to remind you of the input parameters. This is not so important, just 3. I don't know if you can see, it's better to show a movie. So I'm going to try to show this movie. I think it should work. Please tell me, someone tell me if you can see the uplift in the seabed that creates the tsunami, if this image is possible to.
It's moving.
Very good, very good. So I'll go back to the presentation to continue. So one technique that we use here is a technique that was, let's say, started by John T. Rougier, and I've used it in other contexts. So it's to try to build an emulator for the whole time series, but build upon a linear sum of basis functions, and then the leftover, the residual process should be a GP. So this is what I want to show here. Again, with the mouse, it's probably easier. So R is input. So if you have a function of time, but also of the inputs, you can expand this function using basis, so direct products here of functions of the inputs and function of time. So it's a strong assumption in some way, but if you're smart about the type of functions that could be used in order to reproduce the phenomenon of interest as much as possible, then you can probably get away with that assumption quite nicely, and the leftover will be a Gaussian process that soaks up the irregular variations, if you wish. Not noisy, but irregular, non-linear variation. We have a setup for that, a statistical setup that's a bit, that's fast actually, and that doesn't require MCMC, but that's fine. And the other aspect that relates to a general, let's say, approach in model order reduction, the POD, the proper orthogonal decomposition, which is linked to this principal component analysis. So if you want to not use a specific basis, but a tailored basis to the problem. So I'm trying to make my my mouse, sorry, to show my mouse, but I cannot. Okay, so if you want to, oh yes, I can now. If you want to make use of a bespoke basis, not a basis that you would impose upon this output. So here on the left, we use a regular basis, a Fourier basis that we we used in the past for the same phenomenon. So this is the mean that we can capture here, and these are the variability around the mean in some way. But if we use this principal component analysis, but it's a functional one that acknowledges the smoothness, it's a technique in statistics that's quite sophisticated. You can extract even the kinks. You see, you can extract variability that's linked to the actual phenomenon of interest. So this high-dimensional object, this time series, can be thought about as a function, and you can extract the variability around that function in a functional way by accounting for the smoothness. So that's the idea. And if we do that, then we can make use of that in this framework of the outer product method, the expansion that I showed. And if we do so, we do a bit better than using Fourier basis. So you can see on the right side versus the left side, and we can capture the kinks. We can do, we have statistics about the way we do that. And if we want to do insertive propagation, here I'm not showing for the whole time series, but if we have three inputs as parameters, three input parameters, as I showed in the source description, you can propagate these uncertainties to the outputs. I'm just extracting the maximum elevation of this whole time series here, but we can make assumptions here on the inputs. This is expert knowledge. We know, geophysicists know what type of rupture will happen, what kind of probabilistic statement they can make on these ruptures, and therefore we can propagate these uncertainties to the maximum of the time series. So that's what's for time series of outputs. Now we can move on to spatial outputs. So I hope the movie works. So this is a work that I conducted with my PhD student, my former PhD student, conducted on gravity waves. So this is a climate model, the American model CSM extended to the whole atmosphere, WACOM. This is an example of the finest simulations that could be done with that model, going in kilometers up to 450 kilometers roughly in that movie. But you can see the variations of the atmosphere that are generated by so-called gravity waves that I will show a bit more, that I will explain a bit more later. This is very important to model in climate sciences. It's probably the #2 problem after the clouds. Current climate models don't model so well the gravity wave, especially they are breaking in the stratosphere and so on. So if I go to the next step by going back to the presentation. So these waves are generated by flow over orography, meaning mountains and valleys and etc. Convections as well, or fronts that collide into each other. And it's very difficult to do explicit modeling. This model is 1.2 million lines of code, the CSM. Some of you may know this model. And it's at so many levels, that's going up to the upper atmosphere, and it's really difficult, practical. So what we do is we use an expansion again. We replace the output by a projection onto spherical harmonics that are the equivalent of Fourier basis. Maybe I can go faster here because it's not that essential, but we expand the computer model eta onto that basis. And here our goal was slightly different, actually. We wanted to calibrate the model. So this eta means the computer model, the climate model. S is location in space, and theta are these parameters driving the parametrization of the gravity wave phenomenon. And these thetas are slightly unknown. I mean, modelers tune them somehow with some experiments or some prior knowledge, but ideally we want to know the true value of these thetas. What is true here? This is not replicating reality fully, it's just an approximation of reality. But ideally, you want the best theta possible. I'm not going to go into the explanations of how we do calibration, Bayesian calibration. It's too much for today. But what we do is we expand again on that basis. And we do the same for reality, which is not observed, but we observed measurements that are reality plus some noise. And there's a discrepancy also. We acknowledge in that framework of calibration, we acknowledge the fact that there's a discrepancy between what the model can achieve, even tuned at the best values for its parameterization, sorry, versus what reality can include. So we play with all of this. We do calibration, but we try to match observations with model outputs, but we do that on this projection onto this basis. So if we do so, I'm just here skipping the same idea. We assume that these coefficients are themselves quotient process, and if we do so, we obtain these results here that we inferred from a comparison with some observations that I will show you on the next slide. And this is using MCMC in order to make this inference. It takes some time, and these are the 4 parameters of interest. And sometimes we get some values that are narrow enough to be a bit more confident about the actual value that should be chosen, or sometimes a bit wide. And these parameters also have, in some way relate to each other. And if, as a result, this is observation from a so-called reanalysis, where you actually run a model, like some kind of weather model at a very high resolution, using data to assimilating data into it actually. And this is what we managed to produce. It's an improvement upon the current status. We managed to improve by maybe about 15–20% the quality of the modeling, just by comparing observations with model outputs and carrying out this calibration. Now, the last dimension reduction that I want to discuss is this input dimension reduction, where we look at here. It's a different problem. It's again a tsunami problem, where we have an input that's an entire surface. It's the bathymetry. So here you can see that if there is a canyon, or if there's no canyon, this is a nice paper that looks at the tsunami impact at the coast of a canyon in the sea, and it's very large, right? So having precise bathymetry is very important. Now, it's not the case that we have precise bathymetry everywhere. So that's why we have to acknowledge this uncertainty. And this is the case even for the Cascadia that I showed earlier, this region of Northwest Pacific. And so what we do is we again use a basis, but here for the inputs, what we want to do is find a sensitivity, right? We want to, in some way, simplify the input space in order to make use of the most important directions or linear subspace in order to use that as a simplified set of parameters. So what we do, we use the so-called SPD approach for spatial representation of the input surface. We carry out dimension reduction, a very nice technique by Fukumizu and Lang. It's a very, very fast and very nice technique that's gradient based. So we compute gradients in order to see what sensitivity we should expect. It's a bit technical here, but it's working. We have some theorems about it, but we built the emulator on the low dimensional space on which we have projected, and therefore we reduce the dimensionality in that example. In some examples from 3000 to 3, let's say, because a surface is not, even though it's on the mesh and it seems all meaningful. No, actually some variations only are meaningful. We compare with an example where we have exact solutions. By the way, we have adjoint solutions and so on, and we almost do as well, but we do much faster. So this is the exact solution, the active subspace. And we also carry out a numerical analysis of that, generating some bathymetries that are random. And again, I told you from 3000 to 3, and I'm just going to tell you about how fast we learn by training, by using only 100 runs of this complex computer model running on a GPU cluster. With only 150 runs, we managed to pin down what is the subspace we should project onto in order to build the simulator. Yeah, thank you. So if we do that, we manage to project, quickly, and then we can see that, let's say, on the left, on the right side here, we can see that at some locations of interest, the uncertainty is much wider if you account for this uncertainty in the source. If the tsunami earthquake source is the same, the uncertainty, sorry, in the bathymetry. Now, the last point is about composite. So when we have multiple computer model, let's say 2 models fitting into 3, as let's say Ben showed in the UK AEA effort of nuclear fusion, but in climate model is the same, modeling is the same idea. When you have 2 models feeding into another, building an emulator for the global inputs and the global outputs seems the right thing to do. However, you actually waste a lot. It's inefficient, ineffective. I can show you an example of that later. People have thought about this idea. This is a comparison with other studies. We expand upon from work. And what do we do when we have such a structure of a feed-forward system of models? We do by iterations. We take them 2 by 2, and then we project, and then we combine emulators. So we build emulators and then combine emulators. So I'm going to skip the details. There's no time. But what we do is this combination provides a normal approximation of the surrogate model for the whole system. It doesn't look that smart, but actually the exact formulas are possible to get. And if you go on the left, if you look at these 3 functions, I didn't put the functions. These are kind of sine, cosine functions, f1, f2, f3. And if you combine them, you get this function in blue. And if you only exercise the model at some points, on the left and on the right, it's the same exact global inputs. On the left, you only think of the composite emulator from global inputs to global outputs. And you can see that you don't approximate. In green is actually your prediction, your Gaussian process, or let's say here, surrogate model for the whole composite system. But if you use the individual emulators for each of these sub-models, and then you combine them in a smart way, my postdoc has done that, you can see that you gain so much. You understand what's going on in the middle stage, and then you with the same data you can manage to do this. And as a result, you don't need as much runs of this expensive composite model, let's say a climate model or a fusion model, in order to approximate this model by a statistical surrogate, an emulator. Same thing in 2D, fitting into a third. Same thing if you have feedbacks, you can use some nice techniques to remove some feedbacks when they are weak. When the feedbacks are not weak, it's a bit more challenging, but we manage that. And there's a typo here on the right is F2 of F1. But anyways, when you have 2 functions is here, it's an example, but you have global inputs that feed into the second one. You see, the problem of that function is that these points and those points will arrive at almost the same values, and then the design is poor in the second model. So we also provide some kind of design of experiment that is adaptive, and you can see below, using these triangles to add a few runs in the middle will get you a much improved emulator. If one model is much faster to run than the other, let's say 100 times, it happens in a composite model, we gain, in whatever situation, actually, we gain about 30 to 50%. And the last slide is really about this idea of composing 2 emulators, but finding the right design. So you see where you have uncertainty here, if I may annotate, if I may display. So you do want to run the model where you have uncertainty. Oh, sorry. Now I should be able to highlight this. So you see there's uncertainty here. So you want to point there. You see this algorithm does that, and it does that better than the already much better integrated or linked emulator. So now if I go back to full screen to wrap up, we have other examples here, but this is the idea. The integrated emulator or linked emulator learns better, produce better also confidence intervals. I didn't show that, but I didn't highlight that. and cheaper design costs, we can build surrogate models of complex systems of computer models by running a bit more the cheaper ones, or the ones that need to be run more because their functional form requires us to learn about this functional form more. And we can do that together. And now the question is combining that with the dimensional reduction that I talked in the first part of the talk, of the inputs or the outputs, because some of these models propagate high dimensional outputs that become inputs of new model, etc. So there's a lot to do in order to make this happen in realistic systems.